Well, good morning everybody, and welcome to Maths 2 and Happy New Year and all that stuff. I did ask in the chat what anybody felt about the assessment. I see we've got an interesting range of comments. We've not finished marking them all, so I can't tell you how anybody's done yet, but I do have a feel for how the marks are going, which is they're not brilliant, but they're okay. Obviously more information will follow as it comes out. The date for the release, the provisional date for the release of the provisional marks, if I can put it that way, is the 11th of February, so not so far away now. We have a lot of work to do before that. Okay, I will come back to what you thought of the assessment. The assessment for this module, Maths 2, isn't yet decided. It could be in an exam hall, it could be online. And I think we need to bear that in mind as we go through the course, because clearly you've got to be prepared for either. You had slightly less than a week's notice to go from an in-person exam to an online assessment for Maths 1. I can't believe that things will be necessarily any different for Maths 2. So we need to think about that as we're going through the course. Okay, the structure of the course is pretty much like Maths 1. The content obviously is different, but basically we're going to have lectures like this. We'll have a breakout in half an hour or so where we can go through some of the questions. Then after the breakout, I'll go through a tutorial and make sure that some of the questions are answered. At 10 o'clock we've got somebody coming in to talk about the PALs. He is one of the PALs, and he'll be saying what they do, where they are, and that sort of thing. Okay, so if there are any questions now before we start on vectors. It's not looking like there are any questions, in which case let's get started on vectors. So if you go on to I can do it here, can't I? So if you go on to my baseline.org, you might well get Maths 1. You see Maths 1 is popping up at the top here. We're actually on Maths 2 now. So if you type Maths 2, you'll get this. Same sort of layout as before, and we're going to be doing vectors now. So there we go. And did you notice the dollar signs that were on the screen that have now gone? If you get stuck with dollar signs, that will mean that you need to refresh your page. And if you refresh the page, the dollar signs will go away. Okay, so vectors. What on earth is a vector? Let me have a notepad. Now, there are two quantities for those who don't know, and I'm sure plenty of that you do. One is called scalar, and that is a number. So, for instance, if we have a room, there's a room, okay, and if I put a thermometer, let's have it red because it's a thermometer. If I put a thermometer here, I can measure the temperature. That is a scalar quantity. And if I put another thermometer here, I can measure the temperature. That is a scalar quantity. A scalar quantity is a quantity that just has a number. So your temperature, your height, your age, the speed of your car, the air pressure that's around you, the weight of an object, the mass of a star. Any of these things are scalar quantities because it's defined by a number. But if the temperature here and the temperature here were different because of some reason in the room, then we could draw a line between them which goes from one temperature to another temperature. And now it's got two quantities because this is now a vector because it has a d theta, let's call it, which is the change in temperature. So that's the temperature 1, temperature 2, you take the difference of them, and that's d theta. And then you've also got a direction. And the way I've drawn it, the temperature is going up from the first one to the second one. It could be that the temperature's going down. I'm sure you've all seen the weather forecast where you get images of the wind that's blowing over the UK to show you that it's going to rain or sun or whatever it happens to be. And when there's a lot of atmospheric movement, so you've got an area of high pressure and an area of low pressure, you'll see lots of little vectors which are showing the magnitude and direction of the wind that's blowing over the country. So that's a scalar is a number, and a vector is something that has a number and a direction. Some people say magnitude and direction. That's often what you'll see in books. But basically, a scalar is a single quantity. A vector is a multiple quantity. Often it's only two quantities, but sometimes it can be more than that. Okay, so that's the main difference. So let me just go to my notes to make sure I don't forget anything which are there. A vector quantity, yeah, okay, representation. So often you'll draw a vector, so old-fashioned books often draw vectors like that, A, B, C, U, V. So they've got an arrow over their heads. If you're an old-fashioned person, you're welcome to do that. Another way of writing them is sort of enhanced, like that. C, emboldened I should say, rather than enhanced. That's a bit difficult to write, but often in textbooks you'll see them emboldened like that. Or something that I've seen people do is just to write them like that, A, B and C, with just a line over the top of them, just because that's easier to write than the arrows that I've done here. Obviously, if your vector is an X and you put an X bar, that's not X bar, which we'll run into when we start doing statistics. Okay, so the let's move the page up. Come on. Nope, not that. Let's move the page up. That's better. So a vector A, for the moment I'll just put a line over the top of it so you know that I'm talking about a vector A, and that can be written as the X part of it plus the Y part of it. So we would have an axis like that. This is our X and this is our Y, and we've got a bit along here which is AX, and we've got a bit up here which is AY, and then our vector will be there, which is the combination of the AX and the AY, just like we've done before with the polar coordinates and so on. Okay, and as with polar coordinates, the magnitude, which is written like that, and that is equal to the square root of ax squared plus bx squared. Look at it, Control Z, Control Z, ay squared. Okay, so that's the magnitude, and the angle, theta let's call it, which is the angle in there. Theta will not come as any surprise to you. The tangent of that angle is the y value over the x value, or the opposite over the adjacent if you'd prefer. So theta is equal to tan to the minus 1, I'll say a bit more on that in a second, of ay divided by ax. Mathematicians do this, tan to the minus 1, so tan to the minus 1 means the arctangent. That's to say, it's the inverse operation of tangent. So tan theta equals ay over ax. The arctan of ay over ax is equal to theta. But on your calculator, tan to the minus 1 is written as atan. The reason I say that is that a number of people have mistaken that, and they think tan to the minus 1 is like x to the minus 1 or something like that. It isn't. Tan to the minus 1 means the inverse operation of tangent, which is the arctangent. Okay, so that's one way of defining a tangent. Now, there are things called direction cosines. Direction cosines, which are this angle here, let's call that alpha, which is the angle, so alpha is the angle between the vector and the x-axis. Okay, so that's alpha, so let's leave that there. So alpha is the angle here between the vector and the x-axis, and then beta is the angle between the vector and the y-axis. So here is beta. That sits in there. So if we can find alpha, which is what I call theta in the first case, so alpha is the ay divided by ax, the cosine of that, and beta is the cosine of ax divided by ay. So obviously they're inverses of each other, and in 2D you don't generally use the direction cosines. In 3D that's a slightly different matter. Okay, so that's direction cosines. Now the next thing we want to do is adding two vectors. Right, so vector addition. Now if you happen to be in let's say some of the new parts of Philadelphia, for the sake of argument. The old parts of Philadelphia aren't like this, but the new parts are. I only say that because I happen to know Philadelphia. There are lots of American cities like this. So these are blocks, and they talk about East 23rd Street and all that sort of business. But if you were standing here, so that's you, and you wanted to go to this point here, you can walk along one and up one and along one and up one. So you've done one vector, another vector, another vector and another vector. So we've got A and B and C and D. Okay, if however you had a quadcopter, a drone, you could just fly like that, couldn't you? Which we'll call that E. Okay, so how do we get the sum of that? So E is equal to A plus B plus C plus D. Okay, so let's just break that down into a little bit. So what we're saying is that A plus B. Now, so E is equal to AX, I don't need a line over the top of it, plus BX plus AY plus BY, okay, plus, and then I'll get the CX plus DX plus CY plus DY. Okay, so it's no big shock that you can see that if we add the x bit of that, the x bit of that, that will take us from the starting point to the end point. So AX and CX are both real numbers, so let's have a different pen colour. So AX and CX are numbers. BX, as you can see here, is 0, so that can disappear, and DX is also 0, so that can disappear. Okay, so that's given us the X part of it. Now let's look at the Y part. The Y part of A is 0, so that can disappear. The Y part of B is not 0, so that stays. The Y part of C is 0, so that disappears. And the Y part of D is not 0, so that can stay. Which means that the E is now equal to, AX stays, so we've got AX plus CX, which are the two X components, plus the two Y components, which are BX plus DX. And you can see on my scruffy little diagram there that that's going to be true, isn't it? And if you wanted to calculate the magnitude of E, you'd take AX and CX, add them together and square them. You'd take BY and DY, add them together and square them, and then you take the square root. So isn't it BY plus DY? BY plus DY? Yes, 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 thank you. So let's make sure that that's clear. That's Y and that's Y. Yep, you're absolutely right. Thank you for that. Okay, so that's vector addition. So can I give you a quick problem? Let's just move that up there. Let's take a bit of that and we'll come back to you. Come on mouse, where are you? There we are. Control V and make that a bit bigger. Can I give you 5 seconds to do that, please? And that's introduced another bit of terminology that I've not done. So I want to know vector C is equal to A plus B is equal to, okay? Five I plus 10J. Yeah, absolutely right. So we've got 3I and 2I, so that is equal to 5I. We've got 4J and 6J, which is plus 10J. Right, now can I just mention, we've been talking about AX and AY. What we have in addition is the idea of a unit vector, so that is 1 unit long in the X direction. So magnitude is equal to 1 and the direction is the x-axis, and that's a unit vector I. Okay, then we have the idea of a unit vector here. I bet you know how long it is. So a unit vector is 1, the direction is the y-axis, and that's going to be called j. So 3i is 3 times that unit vector there, which obviously is to about here. 4j is 4 times that, which is taking me up to here. Okay, and then b 2i plus 6j, they are unit vectors along the x and y axes. Okay, so when I used ax and cx before, so ax here and cx here, they are the magnitude times the unit vectors, which is what we've put here. Sorry, I didn't say that before. So what have we got? 5i plus 10j? Yes, we have. Okay, everybody happy with that? I don't understand what you've explained links to the questions that... Sorry, Kevin, I don't understand your comment. The questions are more straightforward. Yeah, maybe I've made it a bit more complicated, but I'm just introducing terminology at this point. Let's come back to that, Kevin, because it'll probably become obvious to you as we go along. Okay, next thing I want to look at is vector subtraction. Subtraction. So if you have one vector that goes like that, let's call that A, and another vector C, which would go, let's say it goes up like that, that's B, sorry, not C. Now, instead of adding them, which would give me the vector across the top here, I'm going to turn this one round and move it that way instead. So this is going to be minus B. Okay, so the sum of those two is there. So this is going to be C, where C is equal to A minus B. Okay, and again, it's, you know, if that's you standing there and you walk along to there and then you turn around and come down a bit, it's the same as if you'd walk there. So the vectors are very much a displacement sort of idea. You move from one place to another and you know, you get to the final point. So that's vector subtraction, which is exactly the same as vector addition, only you subtract the quantities instead of adding them. So if I give you a quick problem on that, let's just take that, Control B. So can I give you 5 seconds to do that little problem? So it's A minus B we're looking for. Okay, so we've got 4 minus 6, which is minus 2i, and we've got 5 minus 3, which is going to be plus 2j. Okay, which is what I'm getting in the comments there. Okay, so vector addition, vector subtraction, absolute piece of cake. Nobody's having trouble with that, I'm sure. Now I'd like to do the vector dot product. There are two kinds of ways of multiplying vectors. There's the dot product and the cross product. First of all, we're going to do the dot product. Okay, so for the dot product, we're going to say that a dot b, and they're vectors, and that is equal to ax times bx plus ay times by. Now, let's just look at this for a second. Ax is a magnitude, ay is a magnitude, bx is a magnitude, by is a magnitude. So we've got a number times a number plus a number times a number. So the result is clearly going to be a number. So the vector dot product gives us a scalar. That's to say a number at the end. Okay, so let's just take the example that we had at the top here. So we're going to say let's change my pen colour back to black. Sounds a bit Amy Winehouse, doesn't it? A dot B is equal to, so looking at the numbers here, it's going to be 4 times, let me do that again, 4, I'm using a dot, times 6 plus 5 times 3. Okay, 4 times 6 is 24, 5 times 3 is 15, so that's 24, 39. Okay, so the vector dot product gives us a number at the end, 39. So I'm going to call this equation 1, because I'm going to come back to it in a second. Now, come on mouse, where are you? There it is. Right, there's another definition for the dot product as well. So a dot b is also equal to mod a times mod b times cos theta. Okay, and I'm going to call that equation 2. So another way of finding the dot product is to find the modulus of a, which in this case, let me just move that down a bit, in this case would be 4 squared plus 5 squared, take the square root. Then mod b would be 6 squared plus 3 squared, you take the square root. That gives me mod a and mod b, and then somehow I'd need to find the angle between the two vectors, and then I'd take mod a times mod b times the cosine of the angle, and that would give me a dot b. Okay, now having these two equations is actually quite handy, because the way vectors are often presented, you know ax and bx, you know ay and by, which means that you know these quantities here, you can calculate these quantities here, which means that we've got an easy way of finding the angle between two vectors. So if we take the two vectors that we were talking about before, let's just move that down a bit. Can I give you a couple of seconds to find the angle between A and B? So I'll copy that over again. Let's see if I can just do that. Control V, yes I can. Come on mouse. So, right, so what I'd like you to do is to find the angle between A and B. Well done, Mohammed. But you don't know how I'm going to do the calculations. Right, I don't get the same as Mohammed. So 4, 5, 6, 3. That's 6, which is the square root of those two. That's that, which is the square root of those two. That is equal to, that looks correct. Okay, so theta is equal to a dot b divided by a squared times b squared, which is 25 degrees, just short of. Okay, 4.32 radians. So Ruben, I agree with you, and Uzafir, I agree with you. So Mohammed, you're a bit on the high side there. Okay, right. So are there any questions as to how we do that? I'll leave the spreadsheet over there. So we found the angle there between two vectors. Let's move that over there. Okay, are we all right with that? So let's just review what we've done so far. In 2D, we've identified what a vector is. We've got the x value and the y value from which we can find the magnitude, and we can find the direction, just as we've done for polar coordinates last semester. Then we've done vector addition, vector subtraction, which are really dead easy. Then we've done vector multiplication, one kind of vector multiplication, which is the vector dot product, which gives us a scalar. So in this case we've got a dot b is equal to 39, and then we've got a way of finding the angle between two vectors. Right, are there any questions on that before I get on to the next bit? Because what I'm going to do now is I'm going to move from 2D to 3D. But before I do that, I'd like to show you a quick video. So let's get my video and we'll put that over there.
Let's say you're interested in apples, because you know everyone loves apples, right? So you go to your favorite search engine, type in your query, and just after a fraction of a second you get your result. The question is, how does it work? See, the thing is, web documents are not categorized like in a library. There are millions and millions of documents on the web all across the world on different machines. And to a computer, each of these documents is just a long sequence of words. A computer does not understand the content of a document. We need to abstract it somehow. So how can we find out if two documents are similar by just looking at their words? Imagine we have a very simple document collection that contains only two words, apple and banana. What we do is, we let our computer count the frequency of each word in each of our documents. For example, document 1 mentions apple 4 times and banana only once. In document 2, apple occurs only once and banana 3 times. And document 3 does not contain the word apple at all. Remember vectors from school? That's essentially what we did. We represented our documents as a list of numbers, a document vector. Why? We'll see in a minute. Once we are finished with counting, we create our index. That's a list of all the words of our vocabulary, and we also remember in which documents the words were contained. Of course, a real-world index will get really huge. And here comes the trick. We also turn our search query into a vector, exactly as we did with our documents before. Now we can use our index to look up our documents that contain the word apple. Document 3 did not mention apples, so it's not relevant to our search. And here's the nice thing about vectors. You can draw them. See? Here's document 1, 4 on the red and 1 on the yellow axis. And then we have document 2, 1 on the red and 3 on the yellow axis. And last but not least, there's our query vector. You can see that the angle between our query and document 1 is much smaller. They are closer to each other. So by comparing all the angles, our search engine decides that document 1 is more relevant to our search and returns it as a result. But so far we only consider apples and bananas. What if our vocabulary grows? Let's say we add the word coconut. As you can see, this just adds another axis. We are in 3D now. But our previous vectors do not change at all. Even if we have one axis for every single word we can think of, the principle stays the same. Unfortunately, a computer does not care about higher dimensions. To the computer, it's just a little more computation. So, by creating an index and turning our documents into vectors, we were able to find similar documents by just looking at their angles. It's not magic, it's just computer science.
Okay, it's not magic, it's just computer science. So that's cleared that up for us.
Meet Lynn.
Shut up. Having a video going on there. Right, so now what I want to do is I want to go from 2D to 3D. And to do that, I'm going to use baseline. Right, so let's drag baseline in so I can show you what we're talking about. So let's drag that in there. Okay, let's not have full screen. So the visualization of this is a little bit harder because obviously it's 2D and the screen is it's 3D and the screen is a 2D space. But basically everything is the same as before. So instead of just an X and a Y axis, we've got an X and a Y and a Z axis. Okay, we have a unit vector I along the X axis, a unit vector j along the y-axis, and a unit vector k along the z-axis. Unit vector means the magnitude is 1 and the angle is along the different axes. So our vector A now is equal to ax plus I, ay plus j, az plus k. Okay, and as before, we can do the vector addition. If I can find the mouse so I can move this page. There's the mouse. Okay, there's vector addition. So what we've got here is we've got vector A, which is 6 in the x direction, 5 in the y direction, and 4 in the j direction, and vector B, which is minus 10 in the x direction, plus 5 in the y direction, and minus 5 in the z direction. So it's actually sticking out of the page. So if I grab hold of this, I can rotate it so you can have a, you can sort of see it in 3D. This is on baseline, so you can go and have a look at it. So you can rotate the axes. You can do mad things with the axes, but I'm doing this slowly, trying to make sense of it. So what we're doing is we're adding A to B, and we're getting the result, which is R. That's the R vector there. And it's exactly the same as the 2D vector, just as the previous video said. We've just added on an extra dimension. So before we had A is equal to AXI plus AYJ, and now we've just added AZK. And if we went into 4, 5, 6, 7 dimensions, absolutely no problem. We just add additional terms onto the end of this. So for A plus B, we add the X parts, we add the Y parts, we add the Z parts, and that will give us our solution. Exactly the same, just with an additional term. Though obviously for our poor human brains, it's a little bit harder to remember, or to visualize, I should say, how these things work. Vector subtraction, exactly the same. We've gone up for A, and then B you can see is a vector going in that direction, but I'm subtracting, so I'm traveling in that direction. So the resultant is there, and as before, you can rotate it and you can try and visualize it. Oh my goodness, it's going on. If you rotate these and you get yourself into a mad position, like I've just done there, just refresh the page, and then they all come back to where they started. So you can then move it a little bit more slowly as you visualize what it is in 3 dimensions. Okay, so that's vector subtraction. So it's exactly the same as the 2D case, except we've got an additional term. The dot product, again, exactly the same, except we now have this additional term here, AZ times BZ. And as I've said before, the dot product gives you a number at the end. It's a scalar value. So we've got 4i times 5i plus 6j times 8j plus 5k times 4k, which will give us the answer, whatever it happens to be. And there's the resulting, oh no, there's the angle theta between the two of them. So as before, we can use the equations that we dealt with to find the angles between two vectors in 3 space. Now that is actually magical, because if you think about this, vectors A and B are lying on a plane that goes through the origin in this case. It doesn't have to, but you've got a plane in 3D with 2 lines on them, and you're able to find the angle between 2 lines on a plane that you can't even touch. That is very helpful in lots of different areas of engineering. I can think of several off the top of my head, but they do tend to be mechanical and physics. But if you're looking at the shear plane in a piece of steel that's under a high degree of stress, that can tell you whether it's likely to fail or not. So if you're doing finite element analysis, for instance, you can get right into the interior of the material to find out where failures are likely to start. Okay, so that's finding the angle. But what I'd like to do now is just get onto the vector cross product. I told you there were 2 different types of vector products. The vector cross product, and it's always written with a cross like this. Remember, the dot product was always written with a dot. And the vector cross product is, the definition is here. This is the non-useful definition, if you like, which is A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them times a unit vector which is perpendicular to both of the vectors. So there we've got vector A, the purple one. There we've got vector B, which is the sort of turquoisey one, taupe I think that's called. And you can imagine a plane that is not the XY plane or the XZ plane or the YZ plane. It's another plane in space, and this is a unit vector that is perpendicular to both of those two. It's perpendicular to the plane that those two are sitting on. Okay, so how on earth would you find that? Well, fortunately, there's an easier way to do it. And this goes back to our friends' determinants. So to find A cross B, what we can do is we can create a determinant with ijk on the top row, and then this is A cross B. So A is the first term, so we put the A values in the middle row, and we put the B values on the lower row. And if it was B cross A, then the B terms would go on the middle row, and the A terms would go on the lower row. Okay, so then we multiply those together and we can get values out of it. There are examples in Baseline, so you can have a look at those, but I'm short of time now, so I'm going to stop talking and twang us into breakout rooms. So unless there are any questions, I'll just set up the breakout rooms. How do you find N? Good question, Uzafir. Generally speaking, you don't need to, but if you do need to, then you use, let me bring that back again. So because we've got two definitions of A and B, so we've got A cross B is mod A mod B sine theta times N, and we've got the this version here. Basically what we can do is we can get the magnitude out of this, which is the A mod A times mod B times sine of theta, and that is the magnitude that multiplies the unit vector. So from here, if we just make this into a unity, then we'll know how much I, how much j, and how much k we've got in the unit vector. Does that answer your question? Can you see where I'm going with that? Yeah, okay. So the dot product is used to find some resultant forces. Yeah, if it's a force you're talking about, it's not necessarily a force, Robin, but it gives you the magnitude of it. So if you're in a force 9 gale, you probably don't care where it's coming from, particularly if you're in a yacht. You just know you've got to get your sail down because otherwise it's going to tear. So the dot product is telling you how much force is hitting your sail. As I say, you probably don't care where it's coming from. You just know you've got to take some action quickly, otherwise your boat's going over. But yes, the cross product will also tell you the direction that it's coming from as well. Okay, so I'm going to bash it into breakout room. So I'm going to stop sharing, which is there. I'm going to stop recording, which